I brought Daan with me because actually at last uASC we started discussing about debugging techniques, so this is why we are now presenting this today. Yeah, so we've already heard like lots of different things system security research is about. Like we might write some side channel analysis tools or also some mitigation frameworks, building attacks and so on, doing verification, and most of the time I would say we do things with code that goes beyond what people usually do with code. And another thing is that it's also often hard to debug. So we are, for example, when we do custom binary instrumentation, our instrumentation might interfere with the debugger. Like I'm inserting int3 to jump somewhere and then like GDB breaks. Or we do some compile time and transformations, and this might be easier to debug, but then we do them for a custom RISC-V course and debuggability is gone again. So then we only have raw hardware signals available, for example. We also, in Michael's keynote, we had something about SGX step. So that's not really debugging, because you cannot debug a production enclave, but still you get some information from this, for example, via SGX step. And yeah, we split the debugging process into 2 phases to be able to work better with it. And the first part is that we do need some tracing in some sort. So we need to collect some data because we want to reason about problems or certain properties of our code. And yeah, we brought some examples for this. And when you are done with the tracing, you also want to analyze the data that you generated. So there might be, like if you don't have debugging functionality at all, maybe you want to restore it. Or if you build some mitigation framework, for example, you want to check whether your framework actually does what you think it should do. And to enable reusage of the analyses, we used an established shared format like the VCD. And yeah, Lucas actually talked a bit about something that I also wanted to mention, like intil-pin for tracing purposes. Yeah, so you can do lots of things with pin tools. They are very configurable. And over the time, our debugging stuff also like evolved, and we now have a very configurable pin tool, but sometimes this also like might not help anymore. So once we also found a bug in pin and then we needed something else, we did binary instrumentation anyway, so we just used strace and inserted custom syscalls, for example. And that can also be really helpful to get values during your program execution.
Another example is when developing custom RISC-V cores and executing programs on them. We can also generate a similar trace because, for example, our RISC-V core called Proteus is simulated using a tool called Verilator, and they can emit a VCD trace of the execution while simulating. And then another example that Anna mentioned before is SGX step, where we can also collect some kind of execution trace, which also has some usable information about the program execution. So this is what these traces look like. On the top, we have an example of a trace generated with Intel pin, where we are collecting registers and memory bytes over time. With Proteus or other Verilator-based cores, we can also collect information about registers, but also about decoded instructions and even microarchitectural state. With SGX step, we cannot directly read out registers, but we do have page granular memory accesses, and we have instruction counts and latencies, which we can then use to infer where in the program we are executing. And once we have collected these traces, we can restore debugging functionality. So we made an implementation of the debugger adapter protocol based purely on these TCD files. And then we can single step through the program, set breakpoints, continue to the breakpoints, and see how the registers change. So this way, we can debug programs and check whether our transformed programs or instrumented programs still behave correctly, even though we didn't really have a debugger before. Another thing we can do with these traces is check for null interference by comparing the attacker observable signals under different secret inputs.
Yeah, so today we shared some behind the scenes, but this is definitely not a comprehensive overview, and I'm pretty sure all of you also do debugging stuff from time to time. And I would very welcome you to also come to our poster, because we created a GitHub repository and already collected the things that we knew about that we used during many research projects. And I would encourage you to all add your favorite things. This can be a really small script, just some smaller hack, or using any frameworks like, I don't know, maybe Unicorn or whatever. If you have cool things how to use it there, come talk to us. And yeah, thank you.
Okay. Do we get any questions from the audience? Any questions? Maybe, okay. We'll probably just have one because of the time.
Hi, maybe I just missed this, but do you guys model the specific behavior that you might only see in microarchitectural environments as well? Or what's, for example, the exact definition of L-fans, S-fanses? How do you get the semantics around these instructions that might not be easily traceable by just macro architectural effects?
Yeah, so those things generally depend on the use case. So for some, for example, for memory-centric side channels, we can see everything that we need for the direct leakage, for example, with the pin tool. Yeah, and then, as I said, it depends on what you need to, what kind of data you need to gather, and how you can then analyze it afterwards.
Okay, thank you.
Okay. Because of the limited time, so I think all other remaining questions can be moved to the poster session, right? Okay, let's just thank the speaker one more time.